explicit, Crank-Nicolson and fully implicit schemes. We will conduct an analysis of stability of numerical scheme for non-stationary one-dimensional thermal conductivity equation. Rho C dt by dt is equal to derivative with respect to x of lambda dt by dx. According to the principle of frozen coefficients, the analysis of stability of this nonlinear equation can be replaced with the analysis of linear equation. dt by dt, d capital T by dt, is equal to a, the second derivative of temperature with respect to x second power, where a is equal to lambda divided by rho c, and it is the constant. We consider that A is constant. Let us use the following discretization scheme approximating the heat transfer equation 2.61. T super n plus 1 sub m minus T n m over delta T minus A square brackets of the expression 1 minus F in round brackets T super n sub m plus 1 minus 2t n m plus t n sub m minus 1 over delta x to the second power plus f t super n plus 1 m sub m plus 1 minus t n plus 1 sub m plus t m n plus 1 m minus 1 over delta x second power. For certain specific value of the weighting factor f, the discretization equation reduces to one of different schemes for parabolic differential equations. In particular, when f is equal to 0, this leads to the explicit scheme f equaling 0.5 to the Crank-Nicolson scheme, And when f is equal to identity to the fully implicit scheme. We shall briefly discuss these schemes and finally indicate the fully implicit scheme as our preference. Let us consider two special cases. Explicit scheme. F equals 0. Substituting of the expression capital T super n sub m is equal to lambda to the power n e to the power I alpha m into the corresponding homogeneous difference equation leads to the relation lambda minus 1 over delta t minus a e to the power I alpha minus 2 plus e to the power minus I alpha over delta x to the second power, and it's equal 0. Using Euler's formula, e to the power I alpha is equal to cosinus alpha plus I sinus alpha, we get the following equation from equation 2.64. Lambda of alpha is equal to 1 minus 2a delta t over delta x to the second power multiplied by brackets 1 minus cosinus alpha is equal to 1 minus 4a delta t over delta x to the second power sinus to the second power of alpha over 2. Solving the inequality, the absolute value of lambda of alpha less or equal to 1, we get the necessary condition of stability. Delta t is less or equal delta x to the second power over 2a. The second case is fully implicit scheme. F is equal to 1. Substituting of capital T and m equaling lambda to the power n e to the power I alpha m into the equation 2.63 give the following expression: lambda minus 1 over delta t minus a lambda. In round brackets we have e to the power I alpha minus 2 plus e to the power minus I alpha over delta x to the second power, and it's equal to 0. It leads to the expression alpha of lambda of alpha is equal to 1 over 1 plus 4a delta t divided by x delta x second power and sinus power 2 of alpha over 2. It's obvious that the absolute value of lambda of alpha less or equal 1 at any positive value a. So the necessary condition of stability is satisfied at any time step. We can formulate the following rule. Implicit schemes more often stable in comparison with explicit ones. But at the same time, the process of solution of system of linear algebraic equations, which derive from discretization of the initial equations, becomes very complicated. The initial equations 2.63 can be rewritten as the following. Round brackets 1 plus 2f a delta t over delta x second power multiplied by delta capital T super n plus 1 sub m minus f a delta t over delta x second power delta capital T n plus 1 m plus 1 minus f a delta t over delta x second power delta t super n plus m sub n m minus 1 is equal to delta t super m n sub m, where delta capital T and m is equal to a delta t over delta x2 round brackets t super n sub m plus 1 minus 2 t n m plus t n m minus 1, and it is a solution of explicit form of equation 2.63. Then equation 2.70 take the form A m delta t sub n super n plus 1 sub m is equal to b sub m delta t super n plus 1 sub m plus 1 plus c m delta t n plus 1 m minus 1 plus dm, and in this expression we have the following: am is equal 1 plus 2f a delta t over delta x second power, bm is equal to cm and is equal to f a delta t over delta x second power, and the last term d sub m is equal to delta t super n sub m.